Welcome everybody to the 10th webinar in the Open Building Institute webinar series. Last week we talked about 3D printing. Next week we're talking about open source tools for architecture. Today we're talking about automation, all the different automation aspects of the Seed Eco Home. So let me share my screen and go right into the presentation. So assuming everybody can hear, let's go forward. So view present mode. So we'd like to welcome you to the Open Building Institute project, which is a crowdsourced open source effort to make affordable ecological housing widely accessible. That is the mission, focusing on open source as the base of the platform, and this builds upon the work of machine building by open source Ecology, and culminates with things like Real Houses, a 1,400 square foot build from 2016. It took us 5 days using our parallel swarm build methods to build the house, another 5 days for the greenhouse, a great accomplishment towards effective open source living, a comfortable lifestyle based on open source principles. Here's basically the floor plan, but automation is a big part of that whole effort, in a sense that automation makes life easy if applied wisely. So starting with automation, like we discussed last week about 3D printing. Well, 3D printing is one form of automation, and here we cover things that are more this is the gantry robot that did the 3D printing, just for reference from last week. But what are all the applications that we're interested in this case? Well, it's about a rich and complex ecological system of activity that is easier, that is not a chore for the human operator in that system. Our system includes the greenhouse, the aquaponics, the utilities, everything from the biodigester, PV, heating, ventilation, biogas, energy. Animals, we have chickens and fish, worms as well, for red worms for composting and fish food. Production includes food from the greenhouse, fuel, I'll talk about, and microfactory. Maintenance, there's cleaning, garden care, there's monitoring and remote control. So those are all the different applications that we reach in terms of automation within the framework of the Seed Eco Home and Aquaponic greenhouse. So it's all about making life easy, productive, and fun. Because if we talk about a whole autonomous, complex system, there's just so many different things that have to be taken care of. So you want to design a system to be efficient, and from the get-go design it so it's not running your life, but you're able to enjoy it. So we're setting a limit of about 15 minutes per day per person to take care of all the things that we have to do. Like right now, the aquaponic greenhouse does not take us more than 15 minutes a day to plant and harvest and do everything in there. But at the same time, we have to be very careful about the technology trap, which means that the more technology we have, the more enslaved we are to it, as opposed to enjoying our free time. So we have to use things wisely. And if the technology is very transparent, open, easy to maintain, because one of the things you get into technology is the maintenance time to keep up with all that technology. Well, with open source, we have good inroads into making technology appropriate to truly serve human needs. After all, it's about serving human needs in the best way possible. So in our route, we do a lot of sensing and activating different things in the standard automation procedure. So there's a ton of different sensors that are available that you can get feedback and digitize it, put it into a little microcontroller. So a few dollars you can get things like time, temperature, humidity, light, voltage, current, floats switches, position sensors, cameras, and water sensors like temperature, pH, electric conductivity. A lot of these sensors are really cheap on a dollar scale. There's also a bunch of not so cheap and useful sensors right now, which definitely would lend themselves to open sourcing to reduce the cost. But for example, a dissolved oxygen probe costs you $250. So that's getting a little expensive there. But there's a whole richness of open source sensors out there that projects like the public lab work with, things like spectrometers that you can analyze water samples with, etc. But let's talk about what we do with a sensor. So with a sensor, what you do is you use a little microcontroller, something like an Arduino, which I will talk about, and do very basic things. You can sense things and turn things on and off. You can run motors to provide all kinds of useful functions that happen by the control code on a microcontroller as opposed to you doing that. Or you can go to very complex sequences like a 3D printer. It's got an automated control sequence of a bunch of steps, one after another, that print a 3D printed object. Or, for example, a solar tractor, an autonomously guided tractor. That's a complex application. Or aerial drones. But these are all examples of automation. So how does this work? At the heart of automation, we would have microcontrollers, which are right now widely accessible open source tools out there, which connect with typically like the Arduino as a classic, historic, well-known, historically important open source piece of hardware, basically a small computer with a small little brain on it, small little microprocessor, and you can do a lot of useful things. These cost on the range of $30 or so, or you can get cheap Chinese clones for like $5 or $10. But you put power into it, you got to power this up, you communicate it to it with a USB adapter through your computer, you can connect various types of sensors to the various pins on that controller, and you can make things move. Typically the way things are done is the microcontroller is a delicate thing, it's like a brain. So to move something bulky, you typically need a relay, which is a power handling device. So a small signal will activate a relay which can handle larger power and currents, so you can turn on things like big motors, pumps, lights and fans, and etc. So that's the basics of the system. So I'll talk about how this works and then how we apply it. So to program a microcontroller, it's very simple. You connect to it with a USB cord to your computer, and you can program it. You can upload a program. Now, how do you do a program? Well, one way is you can learn programming. That's one way. And it's not too complex. You write little programs which essentially are like basically instructions. Things like you begin a program, read a sensor pin. If this pin is activated or gives you a certain value, you do one thing. If another condition arises, you do another thing. And you write that in computer code. It can get tricky. Then you upload it to the computer. But it's actually much easier than that. You can have actual visual programming interfaces that you pretty much drag and drop commands like, okay, do this, if this, then that, various loops, start and end sequences. You can do that with a program like open source ArduBlock, and while you do that visually, dragging and dropping your programming language, it appears in another window as the actual computer code. So you don't even have to know programming to use microcontrollers. So it's actually very, very friendly, user-friendly these days, and lots of good instructionals online, and also you can do data logging very easily. What you see here is an Arduino controller on the bottom with a shield, which means a board that plugs right into piggyback onto the Arduino, and that's a data logging shield, which has a memory card, as many gigs as you like, so you can do things like data logging. You can be collecting, for example, temperature or humidity by the program that you wrote. So this is a data logging shield from Adafruit by another open source company. So the modular approach of OSE lends itself to a universal controller. So what we're thinking about is, okay, if there's typically a microcontroller involved, there's a bunch of sensors, there's power in and power out, let's do a generalized version of that that's quite interoperable. And this actually emerges very recently. Like, for example, when we do the brick press controller, and then we compare that to a thing like a controller for the watering, automated watering in a greenhouse, well, you find that you've got so many common pieces. You've got the Arduino, you've got some relays, you've got a sensor, and you've got power. So, well, why not generalize this so we're not making a dedicated device for every application? We could generalize this and adapt it to different functions depending simply upon what computer code we upload to the board. So take a weatherproof box like this. We can 3D print that as well. Program it via USB. You can snap in memory cards in and out if this is about data acquisition. And then any sensor feeds information into this system, and then any device can be connected, whether it's watering, whether it's the super refrigerator, a 3D printer, or a compressed earth block press. So one example is, okay, let's talk about more about universal wiring. We actually are going to Ethernet cables, which are very usable, everywhere obtainable, readily sourceable, universal kind of a wire system. It lends itself well for this, using Cat5 cables, unions and couplers, and splitters, Cat5 splitters and couplers. The advantage is you've got 8 wires per wire, and you can connect so many different things to one wire. With the 8 wires, there's up to 16 amp of carrying capacity per Cat5 cable. So the idea here is what we're doing is this radical parts reduction that we like to think about in open source ecology, and kind of transferring that to Open Building Institute. But basically, minimum number of parts make this very, very redundant, so you can plug anything into anywhere, very universal way. So for example, aquaponic tower watering. Okay, so you're going to have water solenoids, 120 volts AC in, so say you plug this into the power, and you've got your connector that goes to your solenoids, and you can, because it's got 8 wires, you can connect up to 7 water valves. So that means 7 signals and then 1 ground that's common to all of them. But that's an example. And then you've got your Arduino and wiring inside, but that's how it would look. Now in the case, for example, of a compressed earth block press, pretty much identical, except you're feeding in 12 volts DC, and you've got the way a brick press works, it's got a pressure switch that detects pressure and then activates solenoid valves that control the motion of the cylinders inside the brick press. Well, here it is, once again, a brain controller with a different control code that basically works on timing and detection of a pressure, whereas in the automatic watering system you don't have any sensing, because you're just timing it. Here you're timing it in and sensing a pressure in the compressed earth block case. So let's start going to the systems of the aquaponic greenhouse and the seed eco home, starting with water. So we've got surface water catchment. We're not relying on pressurized water from, so this is rooftop and surface water, that's just in the beginnings. We don't have a connection to the utility, so we got to do this ourselves. Well, there's a little bit of things to do. You got to pump water from one place to another to purify it, to create pressure, to run your hydrant, and so forth. So what's the logic involved? Well, water logic is, we have water tanks in our utility room, so the logic is determined by a float switch and a water cisterns and a pressure tank switch. So water cisterns carry 500 gallons of purified water altogether. So the logic there is, every morning and evening the tanks are topped off until a float switch is triggered. And this considers daytime energy use, because part of the deal of the seed eco home is very low energy usage and off-grid operation, which means that we operate as much of our infrastructure during the day when there is light. So in this case, you might have a light sensor that says, okay, daylight came, this is morning now, power is coming into the PV panels, now turn on the water tank, turn on the pump in the pond to start filling the water tanks. So a little bit of sensing there. So once again, your microcontroller, you sense that it's day and you start pumping. And then the water pressure tank, well, that in itself actually does not need a controller by itself, just a plain water pressure tank, which is activated by pressure. If the tank is empty, the pressure switch tells it to go on. Well, in our case, we would actually add a little bit of automation to that in the sense that during the nighttime, we want to switch from filling up the entire tank, which draws energy, to just on-demand water. Say you got to use the sink to brush your teeth or whatever, or you just got to run the kitchen sink or something. That will be on-demand pumped, which is just for that minute or a few minutes that you're using that, as opposed to pumping up a whole pressure tank, which we don't want to do if we've got limited power for the nighttime. So we're really talking about absolute optimization to get away with the smallest minimum battery bank that we can, which is part of the feasibility of the whole seed eco home, because we're saying, okay, we're using only so much energy during the day and hardly any at night. Therefore, we can do that very effectively with minimal battery storage, where energy storage is an issue for off-grid operation. And then last thing on a water system, the outdoor hydrants, that's just a simple on-demand switch, so no microcontroller needed. So that's the water system up to the potable level, where we end up with a small ozonator, which this is an ozonator generates ozone to purify water. It's an advanced method of water treatment. Basically, you have an air pump that goes through an ozonator device, which pumps out ozone gas into your water, and that disinfects the water and makes it pure. So for the ozonator, we do want to have a little control there, little microcontroller, so that you turn the ozonator on, that just turns on, but then you have a delay, like after we run, say, get a glass of water, we want to keep it on for a minute or two to purify the remaining water in the container that this works with. So just a little bit of delay there. And of course you can use a you can use a microcontroller to do that. You can use another simple on delay timer. But since we're talking about all the kinds of things we can do with an Arduino, or a cheap clone of an Arduino, and by the way, if you build you can get really cheap clones of Arduino, or you can actually get the chip itself, isolate the chip, which only costs the actual microcontroller chip costs like $1 or $2. So you can end up building these systems at an extremely low cost. The microprocessor itself on the Arduino is like $30, but just the chip, the microcontroller chip, that's the brain. Everything else around it is the wiring. I mean, just that chip is like $1, so it's extremely affordable to do these kinds of things. Okay, so let's move on to the waste system. In a Seed Eco home, we have the toilet, which is a macerating, separating toilet, which feeds the biodigester. So in that system, we have a macerator pump that's activated after a delay. So you flush the water, and then after a little delay, you will turn on the macerator pump. So the logic is there, wait for the water to flow down into the macerator pump after just a few seconds, and then pump for like 30 seconds or so until you empty everything. But you don't want to run the pump dry because it's not good for the pump. So that's the logic there. So on and timing sequence. Same as for the kitchen sink. So the kitchen sink also feeds the biodigester, and that means we also have another macerator lift pump there. And it's a lift pump because we're lifting up to the stacked biodigester totes that you can listen to more about in a webinar on the utilities. But active pumping is needed, because otherwise, if you did this by gravity, the tanks would have to be underground, and they're not. They're above ground. So in a kitchen sink macerator system, you've got biomass, you got your waste vegetables, everything that are macerated and fed into the biodigester. So what you have is a catchment tank that fills up to a certain level. A level switch is triggered, and at that point the macerator pump activates for like a minute or so to empty the entire catchment tank, and then the cycle waits again until the catchment tank is full. And the catchment tank might be like 5 or 10 gallons or so you're not running the pump so often. And there's a P-trap, so you don't have the smells from the catchment tank going into the kitchen sink. But there is a little bit of automation there. So let's talk next about the heating system. So Hillbilly heater, it's just a passive solar thermal heater, a closed loop system that we're running into the house with a fan radiator. And the logic there is, once it's daytime, it's hot, this is winter, let's say, a certain temperature is reached, you start pumping the fluid into the heat exchanger inside the house, and you are turning on the fan to spread the heat in the house. So you're transferring heat from the greenhouse into the house, which is a simple thermostat controller that works with a radiator that does forced air as well as pumping of the fluid inside this Hillbilly heater. And we'll probably use use antifreeze, so it's freeze-proof for cold winter times. If the top of the greenhouse can get very cold, even if at the bottom you've got the water never freezes, it never really goes below 32, but at the very top there might be some freeze zones. So, okay, so hydronic stove circulation, that's the hydronic wood or pellet stove is used here. So what happens in a stove with automatic controls, we want to control that. We have a small volume of water that once the water reaches a certain temperature, you turn the circulation on. The circulation runs through the hydronic control panel and into the in-floor heating. So basically the only thing is there that once the temperature of the stove gets to a certain degree, in other words, the flame is on, and it goes off when the flame goes out and stuff. But basically, you've got temperature activation and also nighttime operation. You'd want to have that be low, so would be a timer involved that when you know you're hitting nighttime, you're operating at minimum power once again to conserve power over the night, according to our low nighttime usage policy here. So that's the automation there. As far as the thermoelectric generator goes, we have a thermoelectric generator, a machine for producing electricity off the heat of the stove. The way that works, the thermoelectric generators will be placed on top of the stove, and it's fed by thermosiphon from the heat exchanger, and therefore the thermoelectric generator runs simply on stovetop heat, pumped without any pump. It's just convection or thermosiphon. And then we do have this being cooled, and cooled by water from the pond. So once the power is being produced by the thermoelectric generator, that automatically turns on the pond cooling pump. So this is an example of a system that does not need any automation. It's all pretty much passive, because the principles that we're using is by design. You want to design everything to be as simple as possible. So at first you're eliminating any activity that you have to do. Then you think about making it efficient. So things like how you place things, the ergonomics of how you move around in a house, you want to make that optimal. And if not, then outsource it to your animals. Like let your chickens or pigs mow your lawn by eating it, or outsource it to other humans. And then only when that all that fails, you automate. So you go through the next step of the authentic automation using the microcontrollers and electronics to do that. So here the thermoelectric generator is an example of where you don't need a microcontroller. It's passive by design, so that works well. And the notion here was that allow thermosiphon by putting this thermoelectric generator vertically right on top of the stove, so you don't need a pump. Okay, next is the photovoltaics, the whole electricity system. We are getting that automated, but you can say more monitoring, more in the route of monitoring. So we're actually right now, because of our low nighttime energy operation, we want to understand exactly what all the loads that we're using are. So we're currently installing, we have a collaborator from Michigan Tech, Joshua Pierce's group, who's doing an open source power meter that tracks every single power device in the house, and it logs it. So we're logging current and voltage, meaning the power, for every single load in a house. So that's going to be installed on the electronic panel in the house, so that we have data on down to a detailed, like every half hour or 15 minutes of exactly what's happening, so we know when the sun rises, when it sets, how much power we're actually getting from the PV panels. How much are we using? We might think we're using something, but this will actually tell us exactly what we're doing, so that we can know exactly how much of a battery bank we need, how many PV panels are sufficient to do this, so we can optimize the system for the future. Okay, so next item in the Seed Eco Home is the super efficient refrigerator. And to get an overview of all the utility systems in the Seed Eco Home and Aquaponic greenhouse, you can look at our second webinar, which is the utilities, or one of the early webinars. I think it's second or third, so you can get a good overview, but I'm going through all the different systems here. So the super efficient refrigerator is a conversion of a chest freezer to a refrigerator by a microcontroller in this system. So there's a little microcontroller here. That's, once again, it's an Arduino clone, which has a relay, and you're basically sensing the temperature. When a temperature falls to an acceptable level, like say 40 Fahrenheit, you turn the chest freezer off so that it doesn't act as a freezer, but instead it acts as a refrigerator. So another example of a microcontroller that can be generalized. So once again, like all these controllers, like you see, you can buy it off the internet. But once again, if we devise our universal system, all you have to do is upload different code. You have interconnectable sensors, like you would have your temperature sensor that's on a Cat5 cable. You plug it right in, and now you've got your chest freezer to refrigerator conversion using that universal kind of a controller. So that makes a lot of sense for us because we've got so many different sensors and applications that we do. Okay, let's talk about the biodigester now. So this is a diagram from an earlier webinar, and in the red we have the steps of automation that are happening here. So we've already talked about the inlet from the macerator pumps, which feed the system. That means from the flush toilet and from the sink, about 30 seconds and 1 minute each, respectively. So that's already happening from before. It gets fed into the bottom of one of the chambers of the biodigester, and then 5 minutes in the day, really any time, once or twice maybe, you agitate the digester by pumping actively in a circuit like this that breaks apart any surface scum. It agitates everything so there's no dead spots. Everything is alive and active. Because one of the things you can get in a biodigester is, for example, oil films on the top that they totally cake up, and everything gets, it's like an iceberg on top, and activity might stop if you're not mixing things. So you do an automated mixing system. With that, you also have a temperature sensor from the stove, which would, so this biodigester is heated by the hydronic stove that we have. We would every so often buy a temperature measurement, run the heating into this if the temperature falls below a certain level, and we want to keep this like 96 Fahrenheit and up, about. So whenever we fall below our temperature, we have pumping from the hydronic stove with heat from the hydronic stove. That's definitely available in the winter. In the summertime, hopefully it's warm enough. We're going to have to work out the interim days like spring and fall when we may not be having the stove running anymore and it's not hot enough to keep this warm, so we're going to have to kind of work around that somehow. But then here, as far as, so you're filling it in an automated fashion from the sink and toilet, and the overflow is simply by gravity. So that goes into our effluent system, into our drain field, and automatic. So the three different functions here that are controlled, one is happening at the sink and toilet, and the other, and we can perhaps use so now talking about efficiency of how you do this. A microcontroller can handle many different things. So maybe in this case we would have a single microcontroller that's actually connected by the Cat5 wires. In other words, your Ethernet cables, like instead of running internet, you're actually going from one room to the next, controlling your sensors. So you might have a single microcontroller running all these things, like the flushes and the activations of the pumps and the pumping for the temperature. That's not a problem for a single microcontroller. In fact, down the road we might combine even many more of these functions into a single controller, because a single controller could possibly run the entire house. I mean, it's fast. It's not a problem. It's got like 50 or so outlets and inputs. Like if you take an Arduino, you can have a very large number of outputs coming from that. So we're going to balance the interplay of just convenience, like when is it convenient to run more wires to different places versus just making a new independent controller, because then you have to keep track of the wires, which is which, and so forth. But we have the option of controlling many different things using one controller. So I'm not necessarily saying that there's going to be one controller for every single device in this what I'm talking about. Certainly it makes sense to put many things onto one controller. And the reality will play out. So once again, this is really part A. We're designing this, and when the actual build finishes and we get some performance, we will have part B of this webinar. So actually, this is really part A. Prior to this is the design part. We'll do the build and results part later on. So let's now move into the aquaponics. So the aquaponic greenhouses are our towers filled with bok choy and lettuce right now. This was from last year, about February or so, just lush green at the time when all the insects have been knocked out by the cold of the winter, but it of course doesn't kill off the plants because it's above 32 Fahrenheit in a greenhouse. So there's some kale, bok choy, and lettuce here. But one of the issues that I mentioned already before on Aquaponics webinar is the issue of when you're pumping water into all these towers with just a simple on-off pump. Turn it on in the morning, turn it off at night. All the little exits from the main feed pipe, which is only a half inch, we're going out through 1/8 inch little couplers to each of the towers, and those things clog up constantly. So that's to date has been the number one source of the maintenance time on this system. It's like I go up there and have to unclog those plugs frequently. Like right now it's every couple of days. Before it would be like a couple a day in the summer and things like that. So definitely a part that you want to do better with, and the way to do better with that is what we're thinking is we run this as banks of towers. So we can do two things. One would be say we do 6, so this is 22 towers or so. Say we do 5 or 6 water on-off valves, and those happen to be the same ones as you find in a washing machine, and those cost $5 per channel. So to do 5 of those, you'll pay $25 to automate this system, which you see right here in this picture. But basically, you turn on one bank of towers at a time, and the thing to note is you have one pump pumping a bunch of different on-off switches for water, so the water can go into the different towers, but you're using one pump. You're turning on different sets of the towers at a time, so that a single pump now can run just a small number of them, like say 4 towers per pump. And then what that means, you can make the aperture from the 1/2 inch feed line much bigger. You can make it like possibly even 1/2 inch so that you never get the clogs. But if you had 1/2 inch apertures on every single one of these here, of course you would only get through a few of them before you run out of water, and everything else would not be watered. So that's why you got to do it in banks. Now the other way to do it is run a higher pressure pump and still have very tiny apertures, but use a high pressure pump that literally forces any of the congestion out through the system. So 2 ways, either larger apertures or a more pressureful pump. Right now the pump we use doesn't have high pressure. So the only way we could do it with the existing pump that we have right now would be to open up the apertures to much larger, and therefore you never get the clogs because you just don't if you have the apertures large enough. So that's the automated watering system. That'll be the critical thing that makes this absolutely turnkey in terms of the time, because I mean there's been times where it would take me like 15 minutes per single day. I'd say I have to do it twice, so it would take me like 5 or 10 minutes every time, especially if a whole bunch of them are clogged. So it easily takes you like 15 minutes in a day just for that. So next, so what else can we automate here? Well, here we have, so this, I'm just going through a bunch of different things that you can, and the second one here would be misting for cooling. So this would be a higher pressure system, so high pressure small spigots that are misting spigots that would come from another part of the water system just for cooling in the summer. That's one application if you want to cool. You don't necessarily need to cool because of the vents that open up at the top in this greenhouse, so you don't necessarily need that. But we also think that that might be a good idea for integrated pest management if we use a compost tea brew or even a container of soap water that, say the night before we prepare the compost tea, or just put in a pump into a container of either your compost or your soap water, depending on what you want to do for integrated pest management. But the compost tea can be used as pest management. It helps with various diseases, or the soap water that kills off aphids and other things, other soft-bodied creatures. So you can integrate misting with the integrated pest management as an automated system. So we say you run that, you have that prepared, and then you just run that for however, until you empty out, say, a 5-gallon or whatever size of container you have. So you have to do it on a timer, and you want to do that automatically, so it's not one of the many tasks that you're doing. So it might seem kind of like ridiculous. Well, why would you want to do that? Okay, it's just this 5-gallon bucket. Well, you've got that, you've got planting, you've got tons of other things. The number of things that we have going on here are huge. So there's a clear case that automating that will make you not forget that. Because say you forget to say turn on your water one day in a hot day, you literally lost your crop. If you've got a sensitive crop. So next, these 3 new bubbles that opened up, so there was like 5 different spigots for misting, let's say. So every mist head gets like 3 or 4 towers, 4 or so towers. And next is fans. So fans, they would turn on automatically with the day. They don't need a microcontroller. The fans would turn on with the daylight coming out, connected directly to the PV panel. So we use DC fans that blow air around. And air is very important because you get mold and insects galore the less airflow you have. So that's definitely a thing we're seeing right now. We're not running so many fans, and we've got mold all over the place. You can definitely see it, that wherever you don't have air circulation, you see more bugs and mold. That's pretty much in general. Okay, next what you could automate is pumping. So air pumping in the ponds themselves should go on 24/7, but in the daytime you might want to consider running some more to keep the fish more healthy, just load up more oxygen into there, keep the health better and better. So there would be a case for daytime running of more pumps, and those air pumps, and if you had DC air pumps, that would be good. Typically they come in AC, so if they're AC, we want to probably put them on a controller, because then you want to turn that on and off, because the way it works, if you have direct DC loads, they can be connected directly off the photovoltaic panels, and therefore you don't need any control on that. That just comes directly from the DC. But if you have an AC load, you need to have gone through an inverter or something, so you would need to turn that on and off. Just the sunlight coming up and down would not do, because the inverter would be on 24/7. So more things. What would really be also interesting for the greenhouse? So we have a complex system. We've got the chickens in there. We've got redworms. We've tried black soldier fly a little bit. We didn't really like that. But for the redworms, I mean, if you make worm towers, which we're doing in the next greenhouse much more actively, in a 2016 build, which we just completed, it would be very nice to harvest them very effectively, so that you can feed them to the fish or the chickens. Now for the chickens, you can just dump a container of compost with worms in there. They'll pick through that, but you don't want to throw a container of compost into the water necessarily. So you want to separate the redworms. So a nice automated system, some kind of a drum or turning system which separates the worms, that would be awesome. I mean, if you could completely automate that, you can walk away from the system for a month and your fish are fed and everything is happening. So it's just a question of testing the limits of what's possible for a super low maintenance system, where it's really about doing everything that you can to make it as fun, as productive as possible, without that being a chore. So I mean, definitely worm collecting is a chore. I mean, how do you pick them? You'd have to have some kind of a mechanism or some kind of infrastructure. After some time, and if you have a production operation, that's no fun anymore. That's a job, and if we go to the point of doing this as a revenue model, you definitely want to automate as much as possible because you have a lot to work with. If you're doing a commercial operation, there's much more work involved. You want to automate everything that you can. Okay, another good thing that I thought about, and we're probably going to implement this because good open source prior art exists for this. There's the farm bot that's, we won't necessarily use that, but it would be very useful to use a farm bot to seed our trays, our plant trays. Because what we're doing right now is for these trays, we're typically now, like what you see here, we're growing directly in the holes in little net pots, but recently we've been using the deep pots they're called, and planting the lettuce seeds directly into those deep pots and trays, and then putting those plugs with the little pot into the holes. So what you do there is you plant up trays of plants like this, and it would be awesome to have a robot. So something like that's like a 3D printer or like the farm bot. So this is an example of a farm bot, a thing that's planting, weeding, and watering all your plants in this garden right here. So that's an open source machine, but adapt that to be a much smaller version to plant seeds in your little tray. So use the existing vacuum. I believe it has a vacuum airhead so that it picks up a seed and deposits a seed. So it has a seeding mechanism built into the farm bot, so we can definitely apply that for seeding an entire tray. So imagine that you don't even have to worry about the seeding. You plant that just happens every so often. Your machine is programmed to just do that. Every week, let's say, plant out 100 plants or so, or 200 plants, because the numbers do get pretty high. Like in a system that we have right here, there's 1,000 plants. This is 500. On this side, and there's another pond that's another 500, so it's 1,000 plants. If you're in production, you'd be planting about 200 seeds every week. So you can see how a tray system, an automated system like this, would make a lot of sense, and that wouldn't have to take up much space. It would just be a shelf, like a vertical shelf somewhere in your greenhouse to make this happen. Okay, so next item is the duckweed and azolla trough. So we're planning on a large number of troughs filled with azolla and duckweed, which serve as supplemental fish food. So the fish love the duckweed and azolla. That with the red worms, we're exploring the limits of how much we can do to feed the fish 100% with that. Red worms, when you have other inputs, yes, you can. With the azolla and duckweed, there's only a limited amount you can do, but definitely a substantial amount, which I discussed previously in another webinar as far as how much exactly we can do. But the idea here is if you have an automated azolla collection system, you don't want to be going in there. Well, if it's manual, you don't want to be going in there. You've got all these vertically stacked troughs. This is hung on a wall. These are just gutters. What I'm showing is 1, 2, 3, 4, 5, 6, 7, 8, 9 gutters stacked vertically on a wall, each of them filled with water, and they have growing azolla and duckweed in there. Water is pumped in there to provide the nutrients, and then the way, if you do this manually, the plants in there grow, and then you have to harvest it by hand. You put a net in there and take out some azolla and duckweed. Well, that would get really time consuming, so an automated way to do that is simply pump water in, a certain amount of water in, so that there's overflow into the ponds. And if you time the amount of water flow completely, then you can deposit just the right amount, maybe like half or 20%. Like say every few hours you deposit like 20% of the plants, they get eaten up. Because what you want to do is keep a maximum population here so you can have the fast reproduction without the thing getting eaten up by fish, and then you keep depositing little spurts of that, so you're always keeping high population for maximum growth. But that would require very, very concrete timing on many of these different troughs out of many. So you do want to use a microcontroller to get that timing perfectly. So we have to determine this first experimentally, how it actually works, what the timing is, and then we can just put it on a timer with a microcontroller and go from there. So that would be a great addition if that could harvest itself automatic, because otherwise, once again, another task that you'd have to put on your plate. So more greenhouse automation. Right now, the only time pretty much most of the days that I take in my greenhouse is feeding the fish and sometimes unplugging the towers every other day or so, but feeding the fish every day once or twice. So an automatic fish feeder would definitely help you. Sometimes you forget and your fish go hungry, and that's fine for them, but if you want to optimize growth rates, get this on a timer, never forget, and you can literally forget about it and just harvest your fish. So an automatic fish feeder would be a great idea. This is just a simple open source one. We'd like to do a one that can really work well. So chickens. Now the chickens, what you need to do with chickens is open and close the door of the chicken house. This is the greenhouse. This is a door in the back of the little latch in the back of the greenhouse, which they come in and out of, and that predators don't get in during the night, because everyone loves chickens. Humans love chickens, so do raccoons. Even snakes would eat the black snakes here eat the eggs. So we close the door, the chicken door, at night, and that's an automated thing. It's a little thing that really saves you a lot of effort, because sometimes, say it gets dark and you kind of forget about closing the chicken house, and it might be just enough time for a predator to sneak in there or something like that. So very important in terms of the automation, the peace of mind if you've got, once again, many tasks on your hands. So just a few more things that I can think about the greenhouse, which would help us, that we would like to do. Right now we don't have automated window opening, so that would be a good system to design. Right now we've got sliding windows, so you can't do one of these passive simple things like I've seen. We have to change the opening mechanism maybe in the next iteration of the greenhouse to make it openable by these automatic window openers that exist off the shelf, but we don't have that built in yet. That's something we're considering. Mist propagation. So for a nursery operation, softwood cuttings taken in the summer, for example, a lot of them are propagated under mist so that you keep them watered all the time. For example, mulberries are propagated that way, and so are cold temperature kiwis. I've done that before. So a mist propagation system, basically an automatic mister that goes on for like a minute every 15 or 30 minutes to keep the plants very moist. That's another application of the automation. Chicken incubator. There's in a chicken incubator, you're sensing the humidity and temperature inside the incubation chamber, and then you're turning on heat or humidity mechanisms in there, and you're also turning the eggs every so often. So there's a bunch of automation inside that kind of a system, and that would definitely be something we want to automate once we start growing more chickens. Our plan is to grow chickens. Right now, I mean, the overall plan here is that we are building up all these various infrastructures, but we kind of, you can say over the last few years, we've stepped back into the machines and infrastructures and systems, including the construction systems, to make everything feasible. But chicken growing en masse is, we'd like to get back into that sometime as well in the future. That's definitely forthcoming. And a sprout machine. So a sprout machine, I've talked about it as a highly profitable part of an aquaponic greenhouse. You can be growing sprouts for sale, but that requires that you clean the water, have clean water in there. You have pure water coming to that system constantly, so that you don't have germ buildup. So a sprout machine would be an automated system with watering, possibly a fan in there, and just timing. One thing I haven't mentioned is what we are planning to do this year as well, is the automatic chicken solar tractor. So an eco tractor runs autonomously. It goes outside and it could drag things like chicken tractors or pig tractors. So in confined spaces, somewhat free range by the fact that the tractor is moving autonomously. Imagine we have our 1 acre so-called homestead. You've got this chicken tractor, this tractor that runs on hydraulics, but it's powered by the sun, and we're actually planning a workshop on it, so you'll hear more about that. But basically an autonomous solar-powered hydraulic tractor that can pull heavy loads, that can operate with that can do things like actually pulling your chicken tractors or pig tractors, so that you have the safety for your animals, or the animals not getting everywhere else that they're not supposed to be. So that sounds like super high tech, but with open source Arduinos, the kind of technology I described to you, including the capacities for things like automatic guidance, like that comes out of the the open source drones projects like ArduPilot. There's other automatic control motion, GPS guided motion, that systems that are open source, which makes a thing like an autonomous tractor very, very feasible. It's not a far cry at all, and you can do that for not a lot of money, because we have experience with all these stuff and these things, including the hydraulic solenoid valves that would actuate the hydraulic motors in this kind of a tractor. So that's a pretty advanced type of an automation project, but we are planning to do that this year. So in closing here, I'm pretty much I'm running out of juice here, but just to mention a few other applications and thoughts when we talk about applications and using automation wisely. There's definitely a case for the 3D print cluster in a seed eco home, that you can be producing a lot of different useful objects, and you can look at the discussion in the last webinar. So definitely a useful case of productivity there. Another system that would be very good to implement is aerial drone photography, and do that as a time lapse. So think about this: you have an aerial drone that's just programmed to every single morning just go out on its own and take an aerial picture of your house, and then it just lands back on its docking station automatically. You don't even know it's out there. It's happening 100% automatically. It's storing all its images in an SD card, and you have an automatically generated time lapse that shows the transition of the house throughout the whole year. That would be awesome, and that kind of technology is actually quite available. It would take a project to do that, but that technology is all available in open source. So anyone who wants to get involved and do that, let me know. I mean, that I think would be worthwhile, because part of the effort of the Seed Eco Home and Aquaponic Greenhouse is the education and documentation that we're providing to the general public. Next, Internet of Things data collection. So I already mentioned the power measurement, getting the power, the energy usage of every single device in the house, and that includes environmental measurements of temperature, humidity, water quality in the aquaponic system, and in the house just for general environmental performance. How are we doing in terms of the insulation value and moisture in the house, and everything else based on the amount of heating and energy we're putting in. So that we want to implement as well, and if you want to get involved in that, we're going to get to that later on in the year. So join us as an OSE developer. Now, as far as human intervention requirements, you have to think about the whole house system. Like, what else is there? And what are all your maintenance needs? Like, you're going to have to, for example, keep your grass in shape, or your facility in shape, your fencing, lots of things. I mean, you can go through the different things that right now, you could go through 100 different things that you'd have to do around the house, but in the design of your living environment, think about all of that and schedule that and plan for it and automate of it as much of it as you can, so that when you assess that in its entirety, you can have the easiest way to do that, as opposed to you having a lot of different chores on the facility. So create yourself a maintenance schedule, design things first of all to be as efficient as possible, automate that which you can't, outsource it to animals, make your animals do some of the work for you, like one example being chickens mowing your lawn by eating that, or outsource it to other humans. Get help, get help from other people, because I know, like, living here in managing the 30 acres here, it's a lot of work. So you have to think about what you're getting into carefully, but by design you can have a great, amazing operation that's just really productive and fun for you. So that's where part of it is the automation part. So I think that will be about all for this webinar. And just as a closing note, the way we're developing the open source aquaponic greenhouse and the house and all the different technologies here are with dedicated working teams these days. So we transition to an effort where we are focusing on much more focused development efforts as opposed to ad hoc development. So join us. I'll include a link on the OSE development teams. We are recruiting people for that. We are taking applications and interviewing people who are interested in becoming OSE developers, who are really the serious developers interested in collaborative teamwork as part of a global team of people making the Global Village Construction Set and Open Building Institute move forward. So please do consider that when you see this, we're building a team so that we can really get our development to a much higher level. So with that said, I'm going to open up to a couple of questions and see if anyone has that. Any questions? We only have Jay here. So any questions before we wrap up? Let's see here. So I'm not hearing any questions here. Jay, in case you are speaking, I'm not hearing you. So there are some mic issues. Or you might be muted. So in any case, if there are no further questions for today, this will be posted online, and you can then see that and pass this on to your friends, whoever is interested in seeing this. And otherwise, thank you for listening. Sign up to the OSE development teams, and we'll see you in the next webinar. Thank you.